Hello everyone! Today I want to talk to you about the chain rule. Now, as you may know, we use the chain rule when we want to calculate the derivative of complex functions, such as this one right here. When dealing with an expression like this, it may seem difficult or unapproachable, and you may struggle with what to start with. But I promise, it's not actually that hard. Let me prove it to you by solving this example step by step. First of all, the most important thing that you should remember is that with a composite function like this one, you're always going to start with your outside function and then move your way to the inside function. This is the only order that you should follow because doing it in any other way will result in a mistake. Now then, in this expression, the first thing that we should notice is the power function, and this is going to be our starting point. Think of it in the following way. As you read the expression from left to right, this is the first moment where, if you ask yourself, do I immediately know the derivative of this, based on the rules of differentiation? So, the derivative of sine to the third power. And your answer is going to be no. That's when you know you have to apply the chain rule. If it's easier for you to visualize, you can even use the method of substitution. So you're substituting the entire sine function with t. And now you know that you need to calculate the derivative of t to the third power, which is just 3 times t to the second power. By replacing t with the original function, we get 3 times sine of 4x to the third power, and all of that squared. However, it doesn't end there, because when applying the chain rule, your result is essentially the derivative of your outside function multiplied by the derivative of what is left, so basically your inside function. In this case, after dealing with the power function, we are left with sine of 4x to the third power. This is what we have to differentiate by breaking it up into 2 parts, same as we did before. We have our outside function, which is the sine function, and we have the inside function, which is 4x to the third power. The derivative of sine x is cosine x, so this is what we write, except instead of x, we have 4x to the third power. And finally, we are left with 4x to the third power, which, after differentiation, is equal to 12x squared. Let's do another example for good measure. This one is a little trickier, but with enough practice, you will feel confident enough to solve it with ease. To begin with, we have to notice that this expression is in the form of f of x to the power of g of x, meaning that we need to rewrite it to the following. In our case, that looks like this. Notice that we haven't actually changed anything in our function. E and the natural logarithm cancel each other out, so our original function remains the same. The reason why we do this in the first place is because the derivative of e is still e, so it's easier to work with once we begin differentiating the function. Coming back to our problem, we can apply one of the rules for logarithms by putting x plus 1, our exponent, in front. We're now ready to begin differentiating our function. We're using the chain rule once more. Our outside function is e, so the derivative remains the same, and we can simply copy our original function. Next, we multiply that by the derivative of our inside function, which is this entire expression. And as you can see, we're dealing with a product of 2 functions, so we need to apply the product rule. Let me remind you that it is the following. So by applying, we get something like this. Now, the derivative of x plus 1 is simply 1, but our main focus here is on the natural logarithm of the square root of tan x. This, as you may have guessed, is a composite function, and we need to break it up into smaller parts. So our outside function is the natural logarithm. The derivative is usually 1 over x, but in this case we have 1 over the square root of tan x. And now we multiply by the derivative of what is left. As you can see, the square root of tan x is still a composite function, so we need to repeat the process once more. Our outside function here is the square root, and our inside function is simply tan x. So let's use the method of substitution in this case. By replacing tan x with t, we know that we have to differentiate the square root of t. Because this is such a common differentiation, you can either note it down and remember that it is equal to 1 over 2 times the square root of t, or you can rewrite the square root as the exponent of 1/2 and leave it in the form of 1/2 times t to the power of minus 1/2. In this example, I'm using the first option. After replacing t with our original function, we received the following expression. And finally, we already know that the derivative of tan x is 1 over cosine squared x. So let's write that. We can now plug this back in, and this right here is our final result.